In this video, we discuss writing our double integrals in polar coordinates as opposed to rectangular coordinates. We will review polar coordinate conversion formulas. We'll derive an expression for dA in polar coordinates. And we'll discuss why we might want to switch from rectangular coordinates to polar coordinates. And I actually think I'll start with that. So let's say you've got some surface given by z equals f of xy, and it's up here. And you want to integrate z over the region R in the xy plane. So basically you want to evaluate this integral. Well, this integration might be easier in polar coordinates if the integrand is easier to describe in polar coordinates, or if the region R is easier to describe in polar coordinates. And regions are easier to describe in polar coordinates typically if the region is a circular sector, some part of a circle. So let's just review what polar coordinates are, and then we'll come back to this idea. So remember from trig, if I'm representing a point in the xy plane by coordinates xy, I can also represent that point in polar coordinates, r and theta. Now r is a directed distance from the origin. In polar coordinates we call that the pole, and theta is the angle that this line segment makes with the positive x-axis. So just for example, if this is the point x equals 1, y equals 1, in rectangular coordinates, well, if that's 1 and that's 1, the distance from the origin is square root of 2. And remember, the distance from the origin is r, so r is square root of 2. And the angle here in a 1, 1 square root of 2 triangle is 45 degrees. But of course, we don't want to be in degrees in calculus class. We'll call that a fourth of pi over 4 radians. And of course, there are infinitely many ways that we can represent this point. We can add and subtract 2 pi as many times as we want. We even have a convention for letting r be negative, although we won't use that convention often in Calculus 3. But the idea is that we can represent this point in terms of x and y, or we can represent this point in terms of r, that directed distance from the origin, and theta, an angle with what used to be the x-axis and is now called the polar axis. Now, x, y, and r and theta are related, and it's easy to see how they're related if we draw a triangle like this. This side length is x, and this side length is y. Well, just using our trigonometric identities, the definition of sine and cosine, we can write x and y in terms of r and theta pretty easily. We know that sine of theta from right triangle trig and from our mnemonic so katoa is opposite over hypotenuse. And in this triangle, the side opposite theta, that's across from theta, is y, has side length y, and the hypotenuse has length r. So I can take this and solve for y by multiplying both sides by r, and I get y equals r sine of theta. So since it's opposite theta, we get the hypotenuse times sine of theta. Similarly, this side is adjacent to theta, so we're going to get the hypotenuse times cosine of theta. We could derive that similarly. We know cosine, according to SOHCAHTOA, is adjacent over hypotenuse. The adjacent side is x, the hypotenuse is r, and we can take this and solve for x by multiplying both sides by r, and we get x equals r cosine of theta. So this gives us two of our coordinate conversion formulas. If I have r and I have theta and I want to get x and y, well then I can use these formulas. X is our cosine of theta, excuse me, and y is our sine of theta. Now I can also use x and y to find r and theta pretty easily. If I know x and y, I can use the Pythagorean theorem to find r, because this leg squared plus that leg squared is the hypotenuse squared. So I know that x squared plus y squared must be r squared. And the tangent of theta must be opposite over hypotenuse, so y over x. Now you don't want to take the inverse tangent immediately. That's not necessarily going to give you theta because of the domain and range restrictions associated with defining the inverse tangent or the arctangent function. And so what I would typically do is I would use y and x here to figure out what theta could be, and then I look at the value of y and the value of x and I see whether they're positive or negative, and that puts me in the right quadrant, and then I can identify the correct value of theta. So these get us from r and theta back to x and y, and then these get us from x and y to r and theta. So there are lots of ways we can represent these points. We can represent them in polar coordinates, r and theta, or we could represent points in the xy plane in rectangular coordinates. Now most of the time we're in rectangular coordinates, and when we're in Calculus 3, and it actually makes sense that it's called rectangular coordinates, because if we've got some region R in the xy plane, let's say it looks like this. If we're in rectangular coordinates, we take this region and we subdivide it in the x direction into n different subdivisions in the x direction. And m different subdivisions in the y direction. It's not a very good grid, but I hope you get the idea. And what we see are a bunch of rectangles. So it makes sense that we would call this rectangular coordinates. Now if I try to do something similar in polar coordinates, it looks a little different. Because remember, if theta equals a constant, like let's say theta equals 0, that's going to give us this axis. If theta equals pi over 12, we're going to get an angle of pi over 12. If r is positive, we go this way. If r is negative, we go this way. If theta equals a different angle, let's say pi over 4, we get a line that looks like that. If r is positive, we go this way. If r is negative, we go this way. So as theta goes through all the possible values, we end up with a bunch of lines. Oops. They're supposed to go through the origin, if I did a good job with my picture. I'll just make my origin bigger. And r, remember that r is a directed distance from the origin. Or if you look at this, it's even more obvious. If r is equal to a constant, we end up with a circle centered at the origin of radius r. So when r is 0, we're just at the origin. When r is 1, we're in a circle of radius 1. If r is 2, we'll have a x squared plus y squared equals 4. That's a circle of radius 2. R equals 3. We're in a circle of radius 3. If you've ever graphed on polar paper, this is what polar paper looks like. So if r is equal to a constant, we're on one of these circles. If theta is equal to a constant, we're on one of these lines that passes through the origin. So it makes a lot of sense that we would call this rectangular coordinates and this polar coordinates. Okay, So that's our review of polar coordinates and how we go from rectangular to polar and why this is called rectangular. And I think you can kind of see why this is called polar. We seem to have a pole right here. And now let's go back to this. Why might we want to switch to polar coordinates? Well, if a region is easier to describe in polar coordinates, this integral might be easier to evaluate in polar coordinates. Or if f of x, y is easier to describe in polar coordinates, this might be easier to evaluate in polar coordinates. If you're saying to yourself, how will I know when it's easier to describe in polar coordinates? Generally, this is the idea. If the region you are talking about looks like a circle or part of a circle, that region is easier to describe in polar coordinates. Now, if your function f of x, y has an x squared plus y squared in it anywhere, well, every x squared plus y squared can be replaced with r squared, so that would be easier to describe in polar coordinates. So let's write all of this down. We'll say the reason why we switch from rectangular to polar coordinates is to make the integration easier. Okay, now there are two ways that that integration can be made easier. We might want to switch from rectangular to polar if r is easier to describe in polar coordinates. So let's just say switch if one of the following is true. R is easier to describe in polar coordinates, or f of x, y is easier to describe in polar coordinates. And if you're saying to yourself, how will I know when it's easier to describe in polar coordinates? Let's describe that now. R is easier to describe in polar coordinates if R, the region R, is a circle or part of a circle. So we call that a circular sector. Or f of x, y will be easier to describe in polar coordinates if f involves a lot of y's over x, because y over x can be replaced by tan theta, or x squared plus y squared. That's actually more common. Every x squared plus y squared can be replaced with r squared. Just to illustrate this idea, let's look at a circle and try to describe it in polar coordinates and in rectangular coordinates. So let's say we've got a circle of radius 2. And it's centered at the origin. Well, in rectangular coordinates, I've got two options. I can let x go from a function to a function, and I can let y go from a constant to a constant. Or I can let y go from a function to a function, and I can let x go from a constant to a constant. Now, if x goes from a constant to a constant, it goes from -2 to 2. If y goes from a constant to a constant, it goes from -2 to 2 as well. But we can't just put those two together, because if x goes from -2 to 2 and y goes from -2 to 2, we don't get the circle, we get a rectangle. Actually, we get a square. We don't want that square. We want this circle. So we let one of these guys go from a constant to a constant, and the other one has to go from a function to a function. Let's say that x is going from a function to a function. So I draw my rectangles this way. Well, then x is going from this function of x, or x as a function of y on the left, to x as a function of y on the right. And the way we find those functions is we take the equation of the circle, which is x squared plus y squared equals r squared. R is 2, so we get 4. And we solve that for x. So we get x equals the square root of 4 minus y squared, or the negative square root of 4 minus y squared. The positive square root, because I'm subtracting y squared from both sides and then taking the square root, and don't forget the plus or minus. The positive square root corresponds to when x is positive, or possibly 0. So that's this side of the circle. The negative square root is on the other side. So x is going from the negative square root of 4 minus y squared to the positive square root of 4 minus y squared. And remember what that means. When you evaluate this double integral, that means you're going from this function to this function right here. And then you're going to integrate this with respect to x, and you're going to replace all the x's with this function and subtract. And if everything doesn't simplify very nicely, you end up doing a trig substitution to evaluate that integral. And that's very long and involved, as we saw when I did the video for the area, or excuse me, the volume between two surfaces. It takes a really long time. The other option is you could let y go from a function to a function, and let x go from a constant to a constant. In that case, we take that equation and solve for y, but that's not much better. If I solve for y, I get y squared equals 4 minus x squared. So y equals plus or minus the square root of 4 minus x squared. So in that case, y goes from a negative square root, that's the bottom half of the circle, that's where y is negative, to a positive square root, that's the top half. So those are our options. Or I could go to polar coordinates, and this is where it's really cool. Since it's a circle, this is very easy to describe in polar coordinates. I just need r to go from a function to a function, and theta to go from a constant to a constant, where r is going from a function of theta to a function of theta, and theta is going from a constant to a constant, or vice versa. Theta could go from a function of r to a function of r, and r could go from a constant to a constant. Now, most of the time, the way this works is r will go from a function of theta to a function of theta, and theta goes from a constant to a constant. But let's look at this here. In polar coordinates, you remember, if r equals a constant, we're talking about a circle centered at the origin. So these are circles radiating out from the origin. So r equals 0 is right here. R equals 1/2, well, that's like right here. R equals 1 is right here. So if I'm talking about, oops, that should be there. If I'm talking about an interval of r values, if I'm starting at the origin and I'm going all the way out to 2, that's telling me that r is starting at 0 and going out to 2. Meanwhile, theta is an angle, and it's an angle that sweeps around the xy plane. Typically, we start this way, start at the x-axis if our region goes through the x-axis, and it's an angle that sweeps around the xy plane. So we're going to start at theta equals 0, and then that angle is going to sweep from 0 all the way to 2 pi. It's going to sweep from 0 here to 2 pi over there. And look at that. Isn't that nice? Remember, those are constants. Wouldn't you rather have constants for your bounds than that square root and have to do a trig sub like we did in the video for the volume between two surfaces? That was complicated. That was a lot. This is much easier. It's much nicer. It's much more elegant. So this circle is easy to describe this way: constant to constant for r and a constant to constant for theta in polar coordinates. It doesn't make sense to work in rectangular coordinates because this isn't even remotely rectangular. it's difficult to describe in rectangular coordinates, and that means the calculations are going to be harder. So that's an example. If we're integrating over a circular sector like this, it would probably be easier to switch from rectangular to polar coordinates. It's also often easier to work in polar coordinates if f of xy involves an x squared plus y squared or a y over x, so that we can replace x squared plus y squared with r squared, or y over x with tan theta. So those are our options. Now, if I want to switch, if I've decided, I looked at this and I said, this is going to be easier in polar coordinates, there are 3 things that we need to do. You're taking the double integral over r of f of xy dA, and you want to write it in polar coordinates. Well, the first thing you need to do is you need a new description for r. So you need to describe the region of integration r in polar coordinates. Kind of like we just did. Remember, r, those are circles, or radiating out from the origin. R goes from 0 out to some value. Now, if you don't get the whole circle, if you just had the top half of the circle, theta is going to take care of that. Let's say I just had the top half. R would go from 0 to 2, but theta would go from 0 to pi. Theta is an angle that sweeps, so it starts here and ends here. Now, there are lots of different ways I could describe that. Instead of going from 0 to pi, I could go from 2 pi to 3 pi, I could go from 4 pi to 5 pi, I could go from negative 2 pi to negative 1 pi. All of that would be fine. But yeah, I want to describe that interval that way. Theta would take care of the fact that we're talking only about that top half of the circle. But r is, our values are these values here. We want to think of them as circles radiating out from the origin, and theta is an angle that sweeps around the xy planes, usually starting at the x-axis. That's where theta equals 0, and then we sweep around in a counterclockwise direction. So we need a new description for r. And then we need a new integrand. So one way that you can do that is you can replace x with r cosine theta and replace y with r sine theta. And of course, if you have x squared plus y squared anywhere, you can replace x squared plus y squared with r squared. So that sometimes simplifies things. If I take r cosine of theta, square it, and I add r sine of theta squared, simplify, I'm going to get r squared. So we need new bounds, we need an integrand in polar coordinates. I'm just going to write that as f star of r theta. And then this dA has to change. Now dA used to be dx dy. Now we need to write it in terms of r and theta, but dr d theta is not going to cut it. Look at this picture that we drew earlier. Dx dy looks like this. That's delta x times delta y, and we get the area of that piece. But when I drew my polar coordinates, when I drew my polar grid over here, did you notice that even if that change in theta is the same, so maybe I'm talking about that change in theta, the farther I get out from the origin, the larger that area becomes. Look, that area is much larger than that area. So dr times d theta is not going to cut it. If this is delta theta, and that's delta r, we're going to have a problem there. That's not just delta r times delta theta. So to figure out what the area of one of these little pieces is, we're going to use some formulas from trig. So we're going to need a new formula for this over here. And it turns out that there's just a multiplier times dr d theta that gives us dA. So you need your new dA, which we'll put over here. It's something times dr d theta. You need a new integrand, and you need new bounds. So let's derive dA now. We can derive dA I'm going to call it the derivation of delta A by remembering how we find the area of a circular sector. So let's say that this is our circle, and we're trying to find the area of this piece, and that's r, and this is theta, and we want the area of that part of the circle. Well, the area of that part of the circle is, well, it's a fraction of the total area of the circle, and the total area of the circle is pi r squared. But we don't get pi r squared out of this. We're only going to get some part of that. Well, the fraction of pi r squared that we get from this is theta divided by that total central angle for the entire circle. I want to say theta divided by 360, but we need to be in radians. So that's theta divided by 2 pi. And the pi's reduce, and we get 1/2 of r squared times theta. So now let's go back to our polar grid. Here are some r values. I'm trying to make them evenly spaced, but it's difficult to do. And here are some theta values. And we're trying to find, let's just say, the area of that piece right there. Well, in order to find the area of that piece, let's zoom in. Let's say it looks like this. I'm trying to find the area of this piece. If this is R1 and this is R2, the area of this piece is just the area of this larger circular sector minus the area of the smaller circular sector. So we're subtracting that area right there. So I'll have area, I'll call it area sub 2 for that larger area, minus area sub 1, and that's going to be our delta A. Well, area sub 2 is, according to this formula, 1/2 of the larger radius squared times this angle, which I'm going to call delta theta. And then the smaller area, that orange area, is 1/2 the smaller radius squared times delta theta. And we can factor out the 1/2s, and we can factor out, well, the delta theta. I'll factor that off to the right. And then I'll have an r sub 2 squared minus r sub 1 squared. And watch this. That's a difference of squares, so that factors. So this is r sub 2 plus r sub 1 times r sub 2 minus r sub 1. And r sub 2 minus r sub 1, we might call that delta r. So now you're saying to yourself, what's this? What is this? Well, it's the average. It's this r value plus this r value divided by 2. It's the average of those two r values. And then remember, we're going to make our grid very, very thin, make all these pieces infinitely small. So R1 and R2 are almost exactly, they're going to almost be exactly the same because this delta R is going to be so small. So we're going to call this average R value R star. And in the limit, that's just going to be a general R value, and this will be dr, and that will be d theta. So it turns out that the area, when we switch from dx dy to dr d theta, it's not just dr d theta. The area of that little rectangular piece turns out to be r times dr d theta. And I think if we look at our grid, that makes sense. The farther we get from the origin, the larger that area becomes. So, and what is this distance from the origin? Well, it's represented by the average value of r, which I think makes sense. Okay, so that's the idea. You need r in polar coordinates, you need a new integrand in polar coordinates, and you need to replace dA with this. And that will allow us to switch a double integral in rectangular coordinates to a double integral in polar coordinates. And again, the reason why we do that, the reason why we might want to do that, is because the region R might be easier to describe in polar coordinates. So if it's a circle or part of a circle, the region might be easier to describe in polar coordinates. So I might want these to be my bounds instead of having these as my bounds. It also may be the case that f of xy is easier to describe in polar coordinates. If our integrand has an x squared plus y squared in it, or a y over x in it, I'd rather switch all of those x squared plus y squareds to r squared. And that y over x, I might want to write it as tangent of theta. So that's the idea. In the next video, we'll do some examples.